Hello, National 5 Chemists. It's Mr. Morton here. I hope you're all doing really well. Here is our second video on nuclear chemistry. Last time we looked at our three different nuclear particles, or excuse me, three different types of nuclear radiation: alpha particle radiation, beta particle radiation, and gamma ray radiation. Today we're going to be looking at specifically alpha and beta particle radiation in terms of writing them into balanced chemical equations. Now, as we said in last video, all of this radiation that we're talking about, we're actually talking about radioactive particles being emitted from the nucleus of an atom. And the reason why the atoms would want to do this is they're trying to become stable. If there's some sort of radioactive isotope, one of the easiest ways for them to become stable is to remove extra protons or neutrons, or change a proton into a neutron, or vice versa. And in the process of doing this, they release radiation. So let's just have a quick recap on alpha particle radiation. We can think of an alpha particle as a helium nucleus, and therefore it will contain two protons and two neutrons. We learned that last time. When a nucleus of an atom emits an alpha particle radiation, its own atomic number must then decrease by 2, because if it's emitting, if we can see from this little picture here, here's our radioactive nucleus. If it's releasing an alpha particle, then it must be losing 2 protons, and therefore the atomic number will decrease by 2, and it's also releasing 2 neutrons, and therefore the mass number will decrease by 4. So here's an example here. Let's say we had this radioactive isotope, thorium-232, and it is undergoing alpha particle decay. So it has emitted a helium nucleus, or an alpha particle. And here's the notation for an alpha particle: 2 for the atomic number and 4 for the mass number. So what we're thinking about in these nuclear equations, and it'll be a very common theme across this, is all we're trying to do is to balance the mass number and the atomic number on both sides of the chemical equation. So currently on the reactant side, on the left hand side, I have a mass number of 232. On the right hand side, I have a mass number of 4. So obviously 4 is not the same as 232. So in order to balance this out, I'm going to need to have 228 as my mass number being produced on this product side as well. Let's think about the atomic number. I've got the atomic number 90 for thorium, only 2 for helium, so the resulting particle produced here will have an atomic number of 88, because 88 plus 2 will give me a total of 90 on the right hand side, which is a total of 90 on the left hand side, and that's fine. So what element has atomic number 88? What is a new element produced when thorium releases an alpha particle? Well, it releases an alpha particle producing this new element, radium. Now, radium has atomic number 88. We've changed from thorium to a new element because we've lost 2 from our atomic number, changing it from 90 to 88, so we've made a new element. And the mass number, as we said, is 228 as well, because these have to add up to 232. And that's all we're trying to do in these nuclear equations. We're just trying to make them balanced, essentially. And that's what this little bit of note says here. In balanced nuclear equations, the total mass number, top number, on the left hand side of the equation has to be equal to the total mass number on the right hand side of the equation. So 232 here, 4 plus 228 is also 232, so that's balanced, and the same has to be true for the atomic number, 92 and 88. The only other tricky thing with the atomic number is, as we've seen here, if I change the atomic number from 90, which is only the atomic number for thorium, and change it to 88, then I've got a new element. So that's something else to also consider as well. It won't just be thorium on both sides here. I need to be thinking about changing it to a different element. Our second type of radiation is beta particle radiation. Again, this beta particle is emitted, is removed from a radioactive isotope's nucleus. So from the center of the atom, this beta particle is released. And just a little recap from last time, a beta particle is a fast-moving electron which is produced when a neutron is broken down to produce a proton. So here we've got an example here. In the nucleus, one of our neutrons is degrading, breaking down and forming a proton. In order to do that, it has to release this high energy electron. So we're changing to produce a proton when a neutron is broken down. As a result, we can think about, well, what's going to happen to this nucleus that the beta particle was ejected from? Well, if we've produced, which we have, a new proton from a neutron, then the atomic number of the nucleus must increase by 1. I've changed one of these neutrons into a proton and therefore increased the atomic number and therefore changed the type of element that I have. The mass number will not be affected whatsoever because we've just changed from a neutron into a proton and both of those have a mass of 1 anyway. Now here is an example where we've got the radioactive isotope bismuth 212, and that has undergone beta particle decay, so it's had a beta particle ejected from its nucleus, and we've been asked, well, what's going to be produced here? Well, obviously a beta particle is going to be produced, but what effect will that have on this bismuth? What will it change? Remember, all we're doing is balancing the total amount of mass number at the top on both sides and the total amount of atomic number at the bottom on both sides. So currently our mass number on the left hand side is 212. Therefore, the total mass number on the right hand side also needs to be 212. Zero mass so far from the beta particle, so my resulting element produced here is going to also have to have a mass of 212, because 0 plus 212 equals 212, and then we've got 212 on both sides. For the atomic number now, the bottom part, we've got 83 on the left hand side. I need to have 83 on the right hand side. I've currently got 1 negative for my atomic number. Therefore, if I have atomic number 84 for polonium, then if I add 84 and negative 1 together, I'll get a total of 83, which is exactly what I want. I want 83 on both sides, so this has to be 84 to balance out the negative 1. And again, we've already talked about the mass number. That has to be 212 as well. And last type of radiation, gamma ray radiation, doesn't really have any effect on our nuclear equations here. Not really going to be looking at it in much detail whatsoever, other than what's in the slide here. They don't have a mass, they don't have a charge, they don't have an atomic number. They have no effect upon our chemical equation when they are released from the nucleus, so we don't have to worry about writing them into nuclear equations. Let's look at this example here. We've been asked to complete the equation for alpha particle decay. We're starting with this radioactive isotope, bismuth 211, and it's telling us that, well, this bismuth is decaying. It is producing, releasing an alpha particle. So that's going to be the first thing I'm going to want to write in to my product side in my nuclear equation. I'm releasing an alpha particle. Now that is definitely not by any means the entire equation, because as we've talked about, we need to make sure that the total mass number and atomic number on the left hand side is equal to that of the right hand side. So our mass number on the left hand side is 211 and the atomic number is 83. Now that means I need to have the exact same amount of mass and the exact same atomic number on this right hand side. Currently the mass number is only 4 and the atomic number is only 2. So let's start with the atomic number. If I add 81 to 2, I'll produce 83, and that will mean that both sides have an atomic number of 83. So this 81 must be the new atomic number produced. when bismuth undergoes alpha particle decay. It couldn't be 83. It does not stay the same. If it stayed the same, if this was 83 for example, then my total on the right hand side would be 85, not the same as the left hand side, so that would be incorrect. It's definitely 81 because 81 plus 2 is 83. For the mass number, well, the mass is only currently at 4. If I add in 207, that will give me 211, which will be the correct total mass number for both sides. And one last thing is that, well, I have not produced another bismuth element, or atom, I should say. That would not be correct, writing BIN again here, because remember we changed the atomic number from 83 to 81. We've made a new element, and so that new element is atomic number 81, which is thallium, TL. And so by bismuth undergoing alpha particle decay, it has broken down to this new element, which is thallium. I've just noticed I've made a terrible mistake at the top here for the mass number. I'm sure you all spotted that when you're watching along with me. I even wrote it down here what the new mass number should be. It's definitely not 211. See how easy it is to make that mistake. If I add 4 and 211, that would be 215, which is not the total mass on the left hand side. The total mass on the left hand side and the total mass on the right hand side have to be the exact same. So it's quite easy to make silly mistakes here, but we'll just change it and we'll be glad that I spotted it for sure. So that definitely is not 211, it is definitely 207. 4 plus 207, 211, that's correct. 2 plus 81, 83, that's correct. And there we do now have our correct nuclear equation. Right, let's look at the second example here. We're starting off with a sodium atom, and we've been asked to complete this to show the beta particle decay. Beta particle, as we know, is produced in the nucleus of an element when a neutron is broken down into a proton, and at the same time we get this fast moving beta particle or fast moving electron produced. So that's going to be the first thing we're going to want to write in here. Our beta particle is produced when one of the neutrons in the sodium atom is broken down. Electrons don't have a mass and they have got an atomic number of 1 negative or negative 1. So what else is going to be produced here? Well, as we talked about, we need to make sure that the mass number and the atomic numbers are the same on both sides. Currently, our mass number on the left hand side is 24 and the atomic number is 11. I need to have the exact same over here. However, currently our mass number is 0 and our atomic number, not 6, 0, and our atomic number is negative 1. So we're a little bit away from what we need to be. Let's start out first of all with the mass number. Currently the mass is 24 and 0. Well, I'm going to have to add 24 to 0 to get 24. And my mass number is 24 on the new element produced here. And the atomic number, well, atomic number currently I'm at negative 1. I want to be at 11. So if I add 12 to minus 1, I'll get to 11, which is what I want. And therefore, the new atomic number is 12. 12 plus negative 1 is 11. I've got a total of 11 on this side, a total of 11 on that side. Again, same with my masses, correct masses as well. And then I do not have another sodium produced here. I've got a new element because I've changed the atomic number, and atomic number 12 is magnesium. So if this sodium 24 isotope undergoes beta particle decay, it will turn into this magnesium atom. And to finish off the video, here's a couple of more challenging questions than what we've been looking at. However, we're just going to apply the exact same theory, the exact same ideas. We're wanting to make sure our mass numbers are the exact same and our atomic numbers are the exact same, and thinking about, especially in question 1 and 2, both questions, thinking about the type of radiation that we're dealing with and what effect that will have on our element that we're starting with and what will be produced. So pause the video now and have a go at these two questions. Okay, let's go through this first question then. We have got this radioactive decay series. We've got a lot of different steps going on here, and it's asked us to identify isotope X and isotope Y. Let's kind of just focus in on this first little part right now, where we're starting with our thorium 231, and it's changing into this isotope X, and it's told us that we've got beta decay. So at the same time as we're getting this isotope X, we're releasing our electron, this fast moving electron. So we can figure out what isotope X should be just by looking and balancing this equation. The mass numbers need to be the same on both sides. Currently 231 left hand side, it needs to also be 231 on the right hand side, and it is if I just put in 231 for this isotope X. 231 plus 0, 231, balanced, same on both sides. Now let's look at the atomic number. Atomic number of 90 on the left hand side, I need to have a total of 90 on the right hand side. Currently I've got negative 1. If I add 91 and negative 1 together, that will give me a total of 90 for the right hand side, same as the left hand side. We've balanced the equation. Now all I need to do is to go to the data booklet and look up what element has the atomic number 91. It's not thorium, thorium's 90, and I go and I check it out and I figure out that, well, this is protactinium, element 91. So isotope X, let's write it in just down here, isotope X is equal to protactinium, which is Pa 91 231. There is our isotope X. So within the first part of part A. Now let's look at figuring out this bit for isotope Y. What could that be? So it's telling us that we're starting with this isotope Y. It is breaking down into thorium 227, and it's doing that again by beta decay. So I'm getting this thorium produced as my fast moving electron has been released. Now let's work to balance both sides of the equation and figure out what isotope Y is. The total mass number on the right hand side is 227, therefore this isotope Y must also have a mass number of 227. Again, the atomic number on the right hand side has to equal the atomic number on the left hand side. Total atomic number here is 90 plus negative 1, which is a total of 89. And that means that this isotope Y also needs to have an atomic number of 89. And then we just do the exact same thing that we did for isotope X. We say, well, isotope X, in this case isotope Y is equal to 227, atomic number 89, and if I go to the data booklet and look up number 89, it is actinium, which has the symbol AC. And there we are, we have answered part A of this question. Let's go on to part B. Which type of decay occurs between isotope X and isotope Y? Let's just do it down here, and we'll do question 2 underneath. So part B, well, we're starting with this isotope X, which we've already discovered is this protactinium 231, and that is changing into our actinium 227 with atomic number 89. So I'm saying to myself, or you should be saying to yourself, well, what's the difference here? What's changed between the left hand side and the right hand side? Well, I've got 231 as my mass number here, and 227 as the mass number on the right hand side. Well, that's a difference of 4. For the atomic number, I've got 91 going down to 89. That's a difference of 2. This is looking like alpha particle radiation. If I take my protactinium and remove an alpha particle, I will now produce my isotope Y, this actinium, which has got a mass number of 227 and atomic number of 89. And then our last question here is relatively similar to what we've just done there. We're starting with one isotope, this isotope P, and it's telling us that we're going to turn P into Q, into R, into S, and they want to know, well, what's the mass number and atomic number for S? So let's say we're starting with this isotope P. It has atomic number 88 and a mass number of 28. As it changes from P into Q, there is beta particle radiation. So I'm again releasing an electron, which means that my mass number has not changed. It's still 228. No change in my mass number, but the atomic number has increased by 1. It is now increased to 89 because 89 plus negative 1 is 88. So there's my new mass number and atomic number for Q. Let's do the next step. Let's change Q into R. So we've figured out what Q is. Let's do a new equation now. We've got Q 228 89. That is changing into R again by this beta particle radiation. The mass number is staying the exact same. We've got a total mass number on our left hand side of 228. Total mass number 228. But the atomic number 89 on this side, I need a total of 89 on the right hand side. If I just stuck in 89 there, well, 89 plus 1 is 88. That wouldn't be correct. So this atomic number needs to be 90. 90 plus negative 1 is 89. The mass number, atomic number need to be the same both sides. So there's my R. And we'll do one more equation here, changing R to 890 into our last one, S. And again, we've got beta particle decay. No change whatsoever in the mass number, still a total of 228, but the atomic number has again increased by 1 to 91. A total overall though of 90. Started with 90, need to end with 90. So to answer a question, well, what's the atomic number and mass number of isotope 80? Well, the mass number is equal to 228, no change whatsoever across our radioactive decay sequence. The atomic number though has changed. It changed from 88 up to 91. Okay guys, I hope you found that video useful. Next video we're going to move on to look at half-life equations.